Now I want to get to the topic, the main topic of this lecture, this distinguishing two rotations. So let's go back to this thing that we did last time at the end, which is you're at like lawful evil corp, and they're like giving you a test qubit that's either 0 or it's like a very slight rotation of 0. It's like a tiny angle. And we saw with one copy, you're kind of screwed. You have like one-sided success probability about 10 over n squared. We also said like, oh, what if we could get like n copies? And we saw like that's not enough. Like you still had one-sided success probability at most 10 over n, which is still pretty small. But we saw that like with n squared copies, that was great. And in fact, you can get a one-sided, error really small, like 0.00006. Okay, and what I ended on last time was like, this is all true if you can just like, the corporation just gives you like a bunch of copies of the test. But what if you could like break into their offices and steal the test generation machine? So what I mean is, like, possibly they themselves, when they're like making the test, they have some algorithm, test gen, that like maybe takes in one qubit and spits out test, which is either this or this. And maybe you can find this and it's like a physical black box. You're like, dang, I can't figure out what test is. I could like pump in qubits here and get out copies of test, but I can't figure out what it is. Or maybe you somehow get their source code, and their source code is basically, an algorithm that you might call mystery rotation, A. And you kind of know that the algorithm is either this, like rotate by pi over n on A, or maybe it's this, do nothing. Okay, these are effectively the two possibilities for what the test generation is doing. It's either like taking in a qubit and like just doing nothing so it comes out 0, or it's taking a qubit, rotating it a little bit, and it comes out this. And of course, if you could get their like source code in the clear, then you would just look at it with your eyes and see whether it was this one or this one. But it could be that like it's some crazy obfuscated like 10 million line program that like messes around and like you can't tell if it's this one or this one. Or you could just effectively think of it as like a black box. You're like, I don't know how this is working, but it does effectively one of these two things. So you might think that like, well, given that seemingly all I can do with this box is like, I can't understand it or I can't break into it, so I can just like plug in some zeros, get out some copies of tests. Like, how is this different from the previous situation? But it is different. There's like one move that you can do that maybe you didn't think of. And that this move that you can do, you couldn't do when the lawful evil corp just gives you a bunch of copies of test. There's some new move you can do now that you have the test generation box. Does anybody know what it is? Yeah? Yeah, this is one possibility. For example, you can put in superpositions. That's one thing you can do. Or more generally, you can put in stuff that's not just 0. And this might help you. Or what we'll really see is you can put in a qubit, get out the result, and put that qubit back into the box. That's the trick we're actually going to use. So let's try this. Let's make a little algorithm. Now that we stole the box, we'll call it rotation detective. And here it is, new qubit A. 2. Now we'll do like a loop for, t equals 1 up to n over 2. And let's just assume n is even. N is this angle, which in this scenario, we're assuming We're assuming they post on their website. The test is either this one or this one. So you know n. Okay, and then what do? You do mystery rotation on A. Or you take this qubit and you plug it into their black box. And then after that loop is finished, well, you just extract. Let's say extract all, and print yes if the measurement outcome is 1, else print no. Okay, and by the way, this is the one where you're supposed to say yes, and this is the one where you're supposed to say no. And I claim this algorithm works 100% of the time. Can somebody see why it works or say why it works? Yeah. Yeah, exactly right. So I won't write it, but I'll just say it in words. Again, you're like, okay, two cases. We do a two-case analysis. Case one, as suggested, case one is that like the test generation device is really rotating by a tiny bit, pi over n. So that's this case. So we're supposed to say yes in this case. And what happens in this case? Okay, you make ket 0, which is like horizontal. And then n over 2 times, you do this mystery rotation. And we're assuming the mystery rotation really does rotate it. So like it goes tick, 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 n over 2 times until it's actually straight up. Why straight up? Well, that's what it said. Like it rotates by this much each time. You're doing it n over 2 times. So like it eventually rotates by 90 degrees. So in like case yes, I mean, you know, you start with 0 and it eventually gets to 1. On the other hand, in case no, well, let me just say, and then you extract all, and it's ket 1. So 100% of the time you see 1 and you output yes. On the other hand, if it's case no, that's the case where like the test generation algorithm, maybe you don't know it, but actually does nothing. Okay, so then like you make a new qubit, it's in state ket 0, and like n over 2 times, like you do this rotation, but like nothing happens. It just stays 0 the whole time. You extract, you get 0 100% of the time, and you print no, which is correct. Okay, so you amplify this pi over n angle to like a 90-degree angle, and now you're like, oh, 90 degrees, I can perfectly distinguish. And the cool thing is this right here. The number of times you used the distinguisher was like basically n. In fact, n over 2. So here, like if you just use the test generation machine in a naive way of like plugging in a bunch of zeros to get a bunch of copies of test, and then thought about what you can do with a bunch of copies of test, we saw that like n uses of the test generation machine wouldn't suffice in this case. You would need to use it n squared times. But with like access to the machine, we see that you can actually solve it perfectly with like using it n times, even n over 2 times. And this is like a key. I mean, this seems kind of simple, but like this is like a key concept ultimately in quantum algorithms theory. You see, this is some kind of quadratic speedup, you might say. Like if we just found the copies of tests on the table, we would need like n squared copies. But if we actually had the algorithm that generated the test vectors, we would only need like n copies. And it turns out like this quadratic speedup is really the heart of a lot of quantum algorithms. And later in the course, we're going to try to like really soup up this idea, generalize it, make it more applicable in more scenarios. Maybe scenarios where you don't necessarily know this angle, or maybe where you don't know the two vectors you're trying to distinguish. But we're going to basically really try to soup this really simple algorithm up into like a somewhat more powerful algorithm that we'll call rotation estimation. That's my name for it in this course. The real algorithm's name is phase estimation because it works even if they're complex numbers. But again, we're just going to stick with real numbers and real rotations and things. So we'll call it rotation estimation. And this rotation estimation algorithm is like maybe the most important subroutine in all of quantum algorithms. And in a very clear way, it's like behind this like Grover algorithm for SAT. I've mentioned this in words a few times, but this SAT is this famous NP-hard problem where every classical algorithm we know takes 2 to the n time. But with Grover's algorithm, it takes square root 2 to the n time. And this square root is like exactly this speed up. So somehow we'll convert the SAT problem into a problem about distinguishing 2 rotations at a teeny tiny angle, like an angle of like 1 over this amount. And then by the fact that we have this like quantum speed up, that's how it's going to work. This rotation estimation algorithm is even at the heart of how we're going to do the factoring algorithm in the end. There it's like, honestly, more mysterious, like why it's helping. But like when we see Grover's algorithm and other quadratic speedups, it's very clear how it's like coming from this rotation estimation or rotation detective problem. Okay. Yeah. Yeah. Excellent question. The question is basically like, how do we know that like this test generation algorithm really is doing either like this rotation or nothing? Maybe it's doing something else. Or you suggested maybe it's doing a reflection. This I'm not sure it's possible. Like if you know that like, oh no, it could be, yeah. Well, yeah, you're right. It could be either doing nothing or it can be doing a reflection through, yeah, I see what you're saying. So we kind of know that like test is either this or it's this. And like we kind of posited that like the way it works is it takes in a ket 0 thing and either leaves it or rotates it. But you're like, what if it takes in a ket 0 thing and either leaves it or reflects it here? And then like reflecting it a bunch of times, it just flips back and forth between here. Yeah, in that case, we'd be in big trouble. So maybe I didn't write it very clearly here. But in all these like qubit state distinguishing problems we've been talking about so far, like I kind of clearly wrote at the top like promise. Like I promise you, and like you believe this promise, and it's true that like the state is either ket 0 or it's like this rotation of ket 0. And like all the algorithms about distinguishing between these cases will not necessarily work if that promise is violated. Moreover, you have to really just take this promise on faith. Like, there's no way you yourself can kind of check whether the promise is true. Because, like, checking whether the promise is true, I mean, is equivalent to, like, learning what is this unknown qubit, which is much harder. So here, I didn't say it, but let me say it more precisely now. Here, I'm really relying on promise that, like, mystery rotation is one of these 2 things. Or test generation, let's call it test generation. Test generation is either, rotate by pi over n on A, or, do nothing. So as you said, like, if you just knew that, like, test came out and 0 or this other thing, that doesn't necessarily imply this promise, but for this analysis, I do like give you this promise, and like somehow you're allowed to believe this promise. Okay? And again, this is very suspicious because you're like, how could you check this promise? Like if you just have this black box, like how could you be sure that this promise is true? And I just have to, for this analysis, I just have to say like, just accept that this promise is true. It's very similar to like mystery toggles, where we're like, at the very beginning, I said, like, just accept the fact that even though you can't look at the source code of mystery toggles, I promise you, like, it just has, like, statements that look like if A1, then toggle, or if X1, then toggle answer, if X3, then toggle answer. Like, that's a promise. And so a lot of difficulty in quantum algorithms in trying to use this idea is how can you get yourself into a setup where you're really confident this promise is true? And that's actually the difficulty with designing, a little bit philosophically, designing new quantum algorithms. We have these like cool quantum algorithms, like this rotation detective and the toggles detective, that work in a scenario where you have some black box code, and you're sure it's doing either this or that, but you're not sure which. And quantum lets you figure out whether it's doing this or that. But you're like, how do I get into this weird scenario where like I'm 100% sure this mystery code is doing A or B, but I don't know whether it's A or B? That's a very unlikely scenario to be in, which is why there are very few quantum algorithms. Like there's only like a couple of weird situations where somehow people figured out like, oh, like here's how you might get yourself into this situation, and then quantum to the rescue. And like this is what's going on, like Grover's algorithm and the factoring algorithm. And here I just had to like just posit it. Like, friends, we're just going to assume that you have access to this box that either does a rotation or doesn't.
Hello, quantum enthusiasts. It's Future Ryan here. I also have a cold right now, which is why my voice sounds a little bit weird. First of all, thanks for watching. We're halfway done, so congrats on making it to the halfway point. And we're about to get into Grover's algorithm, which is very exciting. I just wanted to add one more technical point to this lesson. So in this lesson, we talked about the mystery rotation, where you were promised that you had a rotation that was either by some small angle, this pi over n, or by 0. And you had to tell which of the two rotations it was. Okay, so that's fine, but we actually know that any one qubit unitary is either a rotation or a reflection. And we didn't talk so much about mystery reflections, so I want to do that now. So this is about distinguishing two rotations. What about distinguishing two reflections? So let me erase this. And yeah, let's now imagine that you have a routine you can call called mystery reflection. And you're promised it does one of two possible reflections. So let's say it either reflects through the green horizontal axis here. I'll make that the second one here. So let's say one possibility is that this is reflect across, well, the green line or across ket 0. And actually, we have a name for this operation. This operation, leaves ket 0 by itself, but it changes ket 1 to negative ket 1. So it puts a minus sign on ket 1. So you could also call this if A, then minus. Okay, so that's the second reflection. The first reflection that I'm going to imagine it might be is this one that reflects through this line here at an angle I'll call theta, but we'll say that theta equals pi over 2n. Okay, so half the angle that we were sort of talking about before. So let me write that here. Second possibility is we're doing reflection through the line at angle theta. Okay. And right, so let's imagine that this is your subroutine that you get to call if you want. You can't look inside to see the source code, but it's either this reflection through the line at angle theta, or it's a reflection across the horizontal axis 0. Okay, and this subroutine, by the way, has the property that if you put in ket 0, then in one case, it'll transform, the first case, it'll transform ket 0 to this vector at angle 2 theta, which is pi over n, which is the angle we were talking about before. Or if it's the second reflection, when you start at ket 0, it'll just stay at ket 0. So it kind of has the same output behavior as before. If you put in ket 0, it either takes it to this new state at angle pi over n, or it leaves it at ket 0, but it's doing it in a different way through this reflection. So how can we tell the difference between these two reflections? Well, one thing you should not do is this thing that we did with the mystery rotation, which is to prepare a qubit in state ket 0 and then just do it n over 2 times or a bunch of times, because in this case, you won't get very far. If you put in ket 0, well, if you're in the reflect across 0 case, then of course, every time you do that, your qubit will just stay ket 0. But if you're in this first case, reflect across this blue line here, well, then every time you do the reflection, it'll switch to here, but then it'll just switch back, and then it'll switch here, and then it'll switch back, and so forth and so on. So you won't ever get the state very far from ket 0, and you won't be able to distinguish things too well. So what is the solution to this problem? The solution is based on the fact that two reflections make a rotation. And so the idea is that we can just throw in our own reflection that we ourselves know about, and that'll turn this mystery reflection into a rotation. So let me explain what I mean by that. Let me see if I can scroll up here. Good. So let's do this, we might call it reflections detective. Okay, so the first thing we'll do is we'll make a new qubit. So that'll give us a qubit in the state ket 0. Okay, and the next thing we're going to do is, let's just say we'll do reflect through ket 0, or do this horizontal reflection. This is like if A then minus ourselves. And then finally, the third step, we'll do the mystery reflection. And what I want to think about is like what happens when you do these two steps together. So this is going to be two reflections. First, a reflection across the horizontal axis, plus this mystery reflection, which is either also a reflection across the horizontal axis or a reflection across this blue line. Now let's imagine it's this case here, it's reflection across 0. Then when we do these two steps together, where are we? Yeah, when we do these two steps together down here, well, they're both reflections across the horizontal axis, so they just undo each other and nothing happens. So in sort of case 2, this just becomes do nothing. Okay, but what about the other case, case 1, this red case here, where mystery reflection actually is reflection across this line at angle theta? Well, as we saw in a previous lesson, if you do 2 consecutive reflections, that's equivalent to a rotation. And it's equivalent to a rotation by twice the angle between the reflection lines. So here this angle is theta. So if we take a point, you know, for example, this one, and we reflect it across the blue line, sorry, if we reflect it across the green line, it stays still, and we reflect it across the blue line, it goes up here to angle 2 theta. And that holds in general. So if you do these two reflections together in case 1, the composite operation is rotation by 2 theta, which is this pi over n. Okay, and the good news here is this is precisely the situation we were in before. We now have transformed this by inserting our own line 2, our own reflection. We've transformed the mystery reflection into a mystery rotation, which is either rotation by 0 or rotation by pi over n. Okay, and so we know exactly how to handle this. All we have to do is, you know, what we did in the previous part of this lesson, which is just repeat this n over 2 times. Okay, and then in case 2, when we start with ket 0, it'll end up at ket 0. And in case 1, if we start with ket 0, it'll end up at ket 1. So if we put a measurement in at the end, we'll be able to tell the difference. Okay, so this is a trick for distinguishing 2 reflections at a small angle. Just throwing your own reflection yourself, and that converts the mystery reflection into a mystery rotation of twice the angle. And then we know how to solve the mystery rotation problem. So this is exactly the idea that's at the heart of the Grover algorithm that we're about to see in the next couple of lessons. So stay tuned.